All right, let's talk about zeroth order kinetics. All right, zeroth order kinetics are reactions for which the rate law is given by rate equals k, or rate is constant, right? Now, the reason we call that zero order kinetics is, remember, the ones we looked at previously, this was first order kinetics, and this is second order kinetics. Right? But if you go back and look at first order kinetics, rate equals k times the concentration of A is really the same as rate equals k times the concentration of A raised to the first power, because you raise something to the first power, it's just the same as A, right? So if we put another equation in here, rate equals k times concentration of A to the 0, right? Remember that anything raised to the 0 power is just 1, right? So k times A to the 0 power is just the same as k times 1. And so that means rate equals k. Okay, so that's why reactions for which the rate law is given by this equation, that's why those are called zero order kinetics, because it's the same thing as this. This is the way we want to write it, because that's much simpler. You don't need to worry about the A to the 0, but that's where the name comes from anyway, in case that seems a little confusing. All right. So if the concentration, well, I was going to say the concentration of the reactant A, but really all of the reactants are not found in the rate equation. So for zeroth order reactions, the rate does not depend on reactant concentrations. It depends on something else, right? And that seems kind of weird. But let's take a look and see how you can have a reaction that's not dependent on reactant concentrations. All right. So generally speaking, reactions that follow zero order kinetics are essentially all reactions that have something to do with catalysis. And if you want to look at catalysis, you can imagine a process where you've got nuts and bolts and they're being assembled into a nut and bolt pair, right? So you might think of this as a reaction that's A plus B goes to some pair AB, right? Now, if you had a factory and there were let's say conveyor belts bringing in a whole bunch of bolts and a whole bunch of nuts, and you had people assembling the nuts and bolts into the pairs, the rate would depend on how quickly you could supply them with the nuts and the bolts. So the rate of the reaction would depend on the concentration of those two reactants, right? But if you had to have some kind of a tool in order to make this work, right? So for example, if these things could only be assembled by using a wrench, and you had, say, 50 workers trying to do this, but you only had 2 wrenches, then the process could only happen as quickly as those 2 wrenches could be used to make the assemblies, right? And it wouldn't matter if you had the nuts and bolts coming in 10 times faster or 100 times faster. It wouldn't matter if you had more workers there. The only thing that would matter is the number of wrenches available, right? And that's going to be the case anytime the amount of nuts and bolts, right, is much larger than the number of wrenches, because in that case, all the nuts and bolts are just going to be sitting around waiting, right? So if you have a situation like that in a chemical reaction, this is analogous to some kind of a catalyzed reaction. We have some kind of a reaction happening, and then you've got some kind of a catalyst that makes it go. In most cases, the concentration of the catalyst is very, very much smaller than the concentration of the reactants. And so at any point during the reaction, all of the catalyst molecules are busy working on that reaction. And most of the reactant molecules are just sort of waiting in line for an opportunity to get at the catalyst. Okay? If you have a situation in which all of the catalyst molecules are active at the same time, and there are a whole bunch of reactant molecules waiting, then we say that the catalyst is saturated, right? The catalyst is handling as much reaction as it possibly can, and all of the reactants are just going to have to wait their turn to get at that particular catalyst. And when that's the case, then the rate is only going to depend on the number of catalyst species, and the reaction rate will not depend on concentration of A and B, and so you get a reaction rate that looks like that, and the K will have something to do with the catalyst. Right. So here's an example. Enzyme catalysis is a good example of this. In this particular case, instead of having two particles we're bringing together to make a larger particle, we've got the opposite. We've got a large particle, and the enzyme is breaking it apart. So you can think of this one in analogous to the one that we had, or in analogy to the one we had before. You can think of this as AB going to A plus B with the work of, with the work of a catalyst. An enzyme is a type of catalyst. So I'll just write enzyme here. All right. So the reactant molecule AB comes and makes contact with the enzyme. It moves into this what's called the active site in the enzyme, and the enzyme kind of twists a little bit, breaks the molecule apart, and then the products are released. And in these reactions, the concentration of the enzyme is always much, much smaller than the concentration of the reactants. And so the rate is determined basically just on how quickly an enzyme molecule can perform this process, and then once it performs the process, it has an empty site and it can accept a new reactant molecule. So the concentration depends just on the concentration of that enzyme and how quickly it can turn over this reaction. All right, so what I wanted to look at here is this is some data for a zero order reaction that that a student, research student here at the college did a couple years ago, and the reaction is the oxidation of glucose, and the reaction takes place using an enzyme called glucose oxidase. And what she was doing was measuring the concentration of oxygen as a function of time. And if you look at the graph, you'll see that there's essentially a linear decay, right? So this is zero order kinetics, and this slope is equal to K. I'm going to get rid of this camera for a minute. At least I think I am. No, sorry, can't figure out how to get rid of that. At least you can still see it, so it's fine. What I wanted to point out with this is that if you have an equation that describes the concentration like this, right? That's going to give you a straight line with a negative slope, right? And if T is large enough, it would seem that you could eventually get a negative concentration, and we know that that doesn't make any sense. So, so what happens down here at the bottom of this graph, and why does this not become negative? Well, what happens is, in order to have zero order kinetics, you have to have a saturated catalyst. And for the catalyst, or in this case an enzyme, right, which is a type of catalyst, in order for the catalyst to be saturated, the concentration of the reactants has to be much, much larger than the concentration of the catalyst, right? And that's true in this first part of the reaction, right? But as you get toward the very end of the reaction, the concentration of the reactants begins to decrease, and toward the end, the catalyst is no longer saturated. And when the catalyst is no longer saturated, you can see that the shape of the curve changes, and it's, instead of being linear, it has kind of a curve to it down here. And so at this point, probably right about here somewhere, the catalyst is no longer saturated, and it's no longer obeying zero order kinetics. So it'll follow zero order kinetics almost to the end of the reaction, and then when the catalyst is no longer saturated, the reaction, the properties of the reaction change. All right, let's look at an example. This is a reaction that takes place inside the catalytic converter of your car, right? Carbon monoxide is a product of the exhaust. Of course, carbon monoxide is toxic, and so the catalytic converter is there to react the carbon monoxide with oxygen, convert it into CO2. CO2, of course, is a greenhouse gas. We don't love CO2, but it's a lot better than carbon monoxide, which is toxic. Okay, so let's take a look at this reaction. We've got a data table with time as our x-coordinate and the concentration of carbon monoxide and the y-coordinate. And I thought it would be nice to try one where I think everything we've done so far has had molarity. In this case, since we've got a gas, we're going to express the concentration in partial pressure. So instead of molarity for the carbon monoxide, we're going to use partial pressure. All the other rules still apply, just different units. All right. So the first question is pretty much always the first question, right? We want to know what the rate constant is, because the rate constant is our key to doing everything else that we want to do, right? So if we've got this graph showing the concentration of reactant as a function of time, we can just find a couple of spots where this line crosses, and looks like, let's see, so it crosses the line right here, so that's an easy point to identify, and crosses the line there, so that's an easy point to identify, right? So then to find the slope, just look at delta y, delta x. And like in first order reactions, the slope is negative k, right? Because the slope is negative and k is always going to be positive. So the slope is just the difference in the y-coordinates, and the partial pressure for that second point is 300 torr, and the first point is first point is 500 torr. And then we divide by the change in the y-coordinates, or excuse me, the x-coordinates, right? So here this is about 170 seconds. And this one here is just past the 50. We'll call it 60 seconds. So in the numerator, we're going to get negative 200 Torr, and in the denominator, we get 110 seconds. And so our slope is negative 1.8 Torr per second. And since the rate constant is negative slope, right? So that would mean that our rate constant is 1.8 Torr per second. Right. Terrific. Okay, let's look at another way to calculate the rate constant from this data. Now, if we've got a data table, just like with all the other ones, if you've got a graph and a data table, you can use either to calculate the slope. And for this one, I'm just going to pick, let's say, point at 25 and 25 seconds and 100 seconds. And so our time is our change in x coordinate, and our partial pressure is our change in y coordinate. So the slope is just going to be 420 Torr minus 555 Torr, and the change in the x coordinate is going to be 100 seconds minus 25 seconds. And so the slope in the numerator, we get negative 135 Torr. In the denominator, we get 75 seconds. So again, that gives us the same result, negative 1.8 Torr per second. And since K is negative slope, K is 1.8 Torr per second. All right. So I would encourage you to go ahead and pick a couple of other pairs, whichever ones you want, and try the same calculation and see what you get. Again, there could be a little bit of, could be some difference due to rounding, but you ought to get something really close to 1.8 Torr per second for all of those different calculations. Okay, another common question is to calculate the concentration at some particular point during the reaction. In this case, it's asking us for the concentration at 175 seconds, right, which is going to be somewhere in this ballpark, right? And you can see it's changing from between 100 and 200. It's changing from 400 to 240, right? 175 seconds will be 3/4 of the way there. So the pressure of carbon monoxide, I don't know, maybe 300, something like that. Yeah. But definitely something between 240 and 420. Right. So let's use our equation and calculate this, see what we get. Concentration, well, instead of concentration, since we're using partial pressures, let's do this. Pressure of carbon monoxide at time t is equal to the initial partial pressure minus kT. So the partial pressure at 300 seconds is equal to 600 Torr minus 1.8 torr per second times 175 seconds. And notice here you have torr per second times seconds, so the seconds cancel out, and our units are in torr. You get 600 torr minus 315 torr. And that ends up being 285 torr, which is terrific. That's just what we had predicted. All right. So fairly simple equation. It's really just working with y equals mx plus b, which is something you've probably done many, many times. So the math for these is pretty simple. Okay. Let's go ahead and do another one. At what time will the partial pressure reach 100 torr? Right. So going down here, we want to know when the pressure is going to decrease all the way to 100. And if you look here, it goes down by about a little less than 200 for every second, every 100 seconds, right? So this needs to go down by less than 200. It needs to go down a little more than 100. So, I don't know, maybe it'll take another 50 seconds or something like that. So maybe at okay, so it may take another 50 seconds or so. So maybe at around 250 seconds, maybe. Right. Maybe 300, right? But certainly not 400 or 500. And obviously it's got to be something more than 200 because we're going further down on that table. All right. So again, let's look at our equation. Right. In this case, we're trying to solve for t. So let's try to get the t by itself by subtracting out the initial concentration on both sides. Right. So this will give us partial pressure of carbon monoxide at time t minus partial pressure of carbon monoxide at T0, right, which is the initial, right, is equal to negative KT. And our target concentration is 100 torr. So 100 torr minus initial concentration 600 torr is equal to negative KT. On the left-hand side, we're going to get negative 500 torr is equal to negative KT. Right? We've got a negative on both sides, so we can just multiply the whole thing by -1. If we multiply both sides by -1, those two negatives will cancel out. Right? And we'll get 500 torr equals KT, and then we can divide both sides by K. And we calculated K a little bit ago. K was 1.8 torr per second. All right. So on the left side, we've got 500 torr divided by K, which is 1.8 torr per second, and that equals T. Okay. And just put that in your calculator. Well, actually, let's mention one other thing first. We'll look at the units here. Right? We've got Torr in the numerator and Torr in the denominator, so those both cancel out. And then you've got seconds in the denominator of the denominator, and when you have something in the denominator of the denominator, it goes back up to the numerator. So if you divide 500 by 1.8, you get 277.8 seconds, right? Or let's call it 278 seconds. Right. And again, that's about what we had predicted. Not exactly, but it's the same ballpark, and that's really what we're looking for. Okay. All right. So, what are the things that we looked at here in this one with zero order kinetics? First thing, simple by definition, those are the reactions for which the rate law is rate equals K, and remember that mathematically that's just the same as rate equals K times A to the 0, and that's why they're called zero order kinetics. Okay, but you don't need to worry about that more complicated form. We'll just write it that way. Okay. Also, zero order reactions usually involve catalysts or enzymes, which are a type of catalyst, and you get zero order kinetics when you have a saturated catalyst. So the reaction rate is really dependent just on the number of catalyst molecules, or sometimes you have a solid catalyst. For solid catalysts, the rate would be dependent on the surface area of the catalyst. But in any case, the rate depends on something other than the concentrations of the reactants. Okay. Right. And when you plot concentration of the reactant as a function of time, you get a straight line, right? Because remember the slope of that is constant, right? Or the slope of that is the rate, and the rate is constant, so you have to have a straight line. And the slope, on one of the slides earlier, I may have written slope equals K. But technically slope is negative K, because the slope is negative and K is positive. Okay. Right. And the equation that relates the concentration of the reactant as a function of time is just A at time t is equal to the initial concentration of A minus KT. And the math for these is really simple, just simple Y equals mx plus B equations. All right, that's zero order kinetics, and we'll be back with another one in a little while. By the way, we've covered everything through the first several sections of the study guide, so you can be doing homework problems on first order, second order, and zero order reaction kinetics. That's most of the study guide, I think. There are a couple, 2 or 3 more sections after that, but that's most of the study guide. So you can and should be doing those study problems at this point.